Hello and welcome. Today we're going to be computing convolution integrals. And I'm going to do two examples. And one of the examples, we're going to do just continuous functions. The second example, we're going to have one discontinuous function. And of course, for this, the discontinuity is going to mean we're going to have to, manage cases as we go along. Okay, so let's just recall what a convolution integral is and how to compute it. What we have here is we're given two functions. We'll call them f of t and g of t. Okay. And one thing about f of t is that f of t is going to be equal to 0. I'll say g of t as well. Both of them are, g of t and f of t are going to be equal to 0 when t is less than 0. So what we can really say, of course, is the domain is going to be t from 0 up to positive infinity. We do this because we're using convolution integrals in the context of solving differential equations or doing signal processing, and we usually have a start point at time 0, and we want to know what happens as time goes forward. You can expand out to look at negative intervals, or negative numbers, but we'll just stick with this. So with that definition, what we can say is the following. We can say that f star g of t is going to be a new function built out of the old function or the original functions we had. And that function is going to be defined as the integral from t of f of t minus c times g c. I use c, which is a Greek letter, to integrate over. So c, I think we call it, it's given the name xi right there. And I just use it because it's a really visually salient Greek letter that you don't mistake for anything else. A lot of people use tau. A lot of people use s. But I'll use xi in this one, and it's Greek. What can I say? All right. Another thing you may also see is that this, you can write it in the different order. So g can be the function where you have t minus c, and f can just be evaluated at c. And so the key here is, what you want to do is, of course, choose what makes the integral easier to compute. Okay, so if one of these is easier than the other, we'll definitely want to go with that. Okay, and I should say also, of course, then, the fact that the order doesn't matter also means that basically f star g is equal to g star f. Order simply doesn't matter. Another thing I would mention here also is that there's another way of defining this same integral when f is equal to 0 and g is equal to 0 for t less than 0. We could also write it the following way: as 0 to infinity of f of t minus c and g of c dc. This infinity there doesn't change anything about our work, but it just it's just a different way of writing it. But I am going to stick with using this one or that one, depending on what's most useful for me at the time, with the t in the upper limit of integration. What's really important, though, about that is we can think of t as basically a fixed parameter in the integral. And it also shows up here as a fixed parameter. We're integrating over c. T is just a fixed value. And of course, the function that we define from it will be defined for every different fixed t value that we choose. But in terms of the actual integration process, we have to think of t as a fixed value that we don't mess with. Okay, all right, so with this, I'd like to start, get a new page here, and start with my first example. So we're going to do this first example, which is going to be a continuous function. So we're going to take my f of t is going to be equal to t, and my g of t is going to be equal to e to the negative t. Okay. Another thing to point out, of course, is that this is for t greater than or equal to 0. Like we said before, f and g are equal to 0 when t is less than 0. Okay? So we're thinking about these functions only defined on their t positive domains. Okay, so the next question then is we want to compute now f convolved with g. This is going to be a new function that we define. We're going to integrate it from 0 to t just like before. And then we're going to have f of t minus xc times g of xc d xc. And I want to evaluate, is this the right one? Or do we want to do this one? All right, so we're going to ask that question. We're going to assess which one will be easier. What I want to try then, of course, is I'll just do this one here really quick. I'll write it in red. We have f is equal to t. So what we're going to do is put t minus c, that is the t function evaluated at t minus c, times e to the negative c d c. And I want to ask, is this easier? I'm going to say it works okay. I think actually, though, this one isn't going to work as well. So I'm going to X that out. What I'd like to do is show you what the other one looks like down here. And I think you can all agree that this will be easier. So here we have 0 to t. And we're going to now evaluate e to the negative t minus c. We're going to evaluate g at t minus c now. And then we're going to have f, which is, of course, just c d c. All right, so with that, I can compute a little bit further, 0 to t. And what I have here is I have an e to the negative t, e to the c, times c d c. And what I can see immediately, though, is that e to the t, there's no c in it, so of course it can move outside the integral, which is going to help us a lot. All right, and from here, we should be able to use integration by parts to solve this problem. There's my e to the negative t, sitting out there doing what it does best. And now, of course, we're going to do an integration by parts. We're going to go 0 to t on that, and then subtract. I'm going to move my picture over a little bit here, and now have e to the c d c right there. All right, so I'm going to give myself some more space here, and continue on working. We have e to the t, and now we have to evaluate our expression. What we really have here is t e to the t minus 0. That's coming from this term here we're evaluating, okay? Then finally, we have to evaluate this one. And of course, the antiderivative of e to the c is just, of course, minus e to the c. And then we just evaluate it at 0 to t and take the difference. And finally, we get that'll be e to the negative t. And then finally we get right here minus e to the t plus 1. Okay, we can simplify this up, and we're going to get t. Now what we're going to do, of course, is we're going to take this and multiply it in to both of those expressions there and this one there. And we're going to get t minus 1 plus e to the negative t. Okay, so this is our new function right here, which is f convolve with g of t, or otherwise known as integral from 0 to t of c e to the negative t minus c d c. That's our final answer for this example. This function, of course, we could maybe play around with, what the graph of this looks like, just to sort of see what it looks like. So f star g, what does it look like? So and we're going to look, of course, at time going forward here. We're going to start at 0. And when we're at 0, what we're going to start at is 0, of course, at t equals 0. And then as we go forward, where are we headed here? Well, we clearly see that there is this t here, so we want to say that maybe it just a line that goes upward, right? And I think that that certainly looks like it's going to conform to that line eventually. But what first has to happen, of course, is what we see, though, of course, is there's this minus 1. So we actually see there's another line, if we just move it down a little bit, that goes right there, that crosses through 1 and goes up like that. Okay, so this is the line t minus 1. That's the line t. So clearly that's what we're doing here then. Our curve, if we really look at our curve starts there. And what happens is this part, of course, decays. And what we're going to get is something like this. So that is f star g of t. It's going to eventually move on to the line of t minus 1, but it takes a little time to get there. So, of course, what does this mean? What are we computing here? Well, we'll worry about that later. Right now, we're just worried about how do we compute a convolution integral, and I think we've achieved that goal here. All right, so what I want to do next is now talk about a new integral. And now we're going to do our next example. And now my f of t is going to be e to the negative t again. But my g of t is going to be what we call the Heaviside step function, but evaluated at 3, or shifted by 3. So this is the function, of course, that is 0 when t is less than 3, and it switches on to 1 when t is greater than or equal to 3. Okay, so it's just a little jump up, a little step function. Okay, so it's 0 beforehand, all the way starting at 0, 1, 2, 3, and then it jumps up afterwards. All right, so for this one, we're going to have to do a little bit more work, and this is a little bit more skillful presentation, or a skillful calculation we have to do with our integral. All right, so we're going to have f of, we're going to compute now, well, undo there, we have to go our convolution notation, this big star symbol, it's like an asterisk. We're going to do an integral, and again we have to ask the question, which one do we want? I'm going to take e to the negative t minus c. I'll do this as the f of t minus c here. I'll move that for a second here, actually. That'll be f of t minus c there, right? So that is right there. All right, and then, of course, we're going to have now h of c minus 3, dc. All right, so this is our convolution integral, and clearly we have cases. And the cases are as follows, right? So what we can see, of course, here is that we're integrating from c equals 0 up to t, which we can think of as basically the present time. So the question then, of course, is if t is less than 3, then of course c is also going to be less than 3. And that implies, of course, that h of c less than 3 will be 0. All right. And then, of course, if t is greater than 3, then sometimes, of course, we're actually going to get c is going to be less than 3, and other times c is going to be greater than 3, because, of course, we're integrating from c from 0 up to t. Right, so this, of course, will make we have to basically break down our integral into two cases we will compute separately. And it means, of course, that f star g is going to be piecewise defined. Is piecewise, just like its constituent functions. But that's okay. Again, the whole point here is that we want to take our function, our step function, we're going to convolve it against this continuous function e to the negative t, and we expect, of course, that when we're integrating, we're going to have to worry about what the t value is at time, because, again, just like anything in the real world, we're trying to model things that are turning on or turning off at a certain time. In this case, basically, we have something that's turning on at t equals 3. So clearly that's going to be the dividing line between two different behaviors of my function. All right. Let's now see if we can give ourselves a little bit more space and give this a try. So what we're going to do, of course, is look at case 1, where t is less than 3, in which case, of course, h of c of 3 will be 0. This is a very simple case, and that means, of course, that f star g of t is going to be the integral from 0 to t of e to the negative t minus c quantity times 0 d c, in which case the answer is, of course, just, drum roll, 0. All right. So that wasn't too hard. All right. So in the next case, though, I'm going to have to think about this a little bit harder. I'll move up a little bit more. Now we'll go to case 2, which is now t greater than or equal to 3. What we're going to have to do, of course, is write our integral this way: 0 to t of e to the negative quantity t minus c times h of c minus 3 d c. And what we have to do here, and this is the really important point, this is the point that we have to worry about here, is what this means, this case means that basically c is integrating from 0 up to 3 and then beyond. So what we're going to have to do is break our integral into 3 pieces, or 2 pieces. So first we're going to integrate from 0 to 3, e to the negative t minus c. And on that domain, of course, h is 0, d c. And then from 3, we're going to go all the way up to t. And here in this case, our convolution integral is going to look like this. And then the step function will have turned on at that point. There, that is now h equals 1. We're on dc. All right. So with this, of course, we can see immediately that this part is still 0 there. So we're good there. And now we can, of course, move along here. And I'll continue calculating. I won't need much space for this. This is going to be e to the negative t comes out. We have our 3 and our t and our e to the c dc. And of course, that's going to be e to the negative t. And then we're going to have e to the c is the antiderivative. We evaluated at t and at 3 and t, take the difference. And of course, we're going to get e to the negative t times e to the t minus e to the 3. All right. Well, one way to see this, and now I'm going to bring this back here to our beginning. Sorry if I'm covering up some of the work, but at least on YouTube you can rewind. Is we have e to the negative t, I'm just writing it over again, times e to the t minus e to the 3. What we're seeing here is that this is actually going to be 1 minus. Again, when we multiply this to that, we get 1. And then I multiply that in, and I get e to the 3, e to the negative t. I can rewrite that as actually 1 minus e to the negative t minus 3. And that's a really great answer. Okay, so to put this all together then, if I take this result here and that result there, and I'm going to go find a little spot on my board to put my final answer, my f convolved with g in this case is going to be a piecewise function. So I want to write it like this, and I want to be precise when I say what the function is, that it actually has two parts that are take on these values at different time points. And to be precise, we'll say that it goes from 0 up to 3. And then we have a 1 minus e to the negative t minus 3. And that's for t greater than or equal to 3. What is this graph? What does the graph of this function look like? Well, at 1, 2, 3, we're going to be 0 everywhere. And at 3, you can see that we have a continuous function. It's going to look like this. So here is 1 up there, and you can see that you can think of this as sort of an asymptote that we're going to hit. What we have here is a function that goes like this. It asymptotes to 1. Okay, so that's the 1 minus e to the negative t minus 3 taking over. Okay, so this makes sense for a function that has this heaviside. It's off till t equals 3. And at that point, it turns on, and then something happens, and we get this function here that represents that function over all t values, starting from 0 up past 3. Okay, well, I hope this short video where we just do a couple of convolution integrals, I think the real key here is to be very skillful with your use of integration and managing the limits of integration. That is the key for this. Most students, if they flub this up, is because they're not really being careful with managing their limits of integration and what values the functions in the integral are taking on at different values of t. You have to be pretty precise about that and really pay attention to it. And I think it just takes some practice. Hopefully this video gets you that practice. Thank you so much.